Hi everyone, my name is Xinyu. Today I'm going to introduce the Discrete Cosin TransFormer for image modeling from frequency domain. In this work, we propose Discrete Cosin TransFormer that directly learns semantics from DCT-based frequency domain representation. To achieve the desired efficiency-effectiveness trade-off, we leverage an input information compression on its frequency domain representation, which highlights the visually significant signals. The DCFormer achieves better efficiency-effectiveness trade-off comparing with many RGB models, as shown here in this figure. Our model first takes RGB images as input, converting it to DCT-based frequency representation, followed by an optional frequency compression module. The compression module offers significant efficiency boost with slightly performance trade-off. The frequency-based representation is then augmented with positional and frequency embedding and feed into a set of DCFormer blocks. The frequency attention is compatible with various transformer attentions, including swing attention, neighbor attention, and others. A linear projection with cross-entropy loss is used for classification, and the MSE reconstruction loss is used as an aux loss when frequency compression is applied. We study several frequency domain compression strategies and empirically choose the zigzag-based hard selection for compression, as it works best without introducing additional computational cost. The cross-attention based soft selection is deprecated since it's computationally expensive. Average pooling-based approaches performs the worst because averaging frequency responses over different frequency bands doesn't make sense. We conduct experiments on multiple datasets and various tasks. We show a few results here, and please refer to the paper for details. On ImageNet classification tasks, the DCFormer significantly outperforms the previous frequency domain-based approaches by a significant margin with less flops, as shown in blue. Benefits from the proposed frequency domain compression. By increasing the input resolution while performing the input compression, we see performance increase, as shown in green. It's also worth mentioning that the DCFormer without input compression achieves similar performance compared with the same backbone takes RGB inputs. This proves that the transformer can learn semantics from frequency representations directly without performance compromise. We further test the DCFormer on object detection and instance segmentation tasks. On object detection, given the same input image resolution, the DCFormer achieves slightly worse performance compared with the SOTA RGB models, but with 15% less flops. By scaling up the input image by 1.5 times, the DCFormer is able to achieve comparable performance, but still with 11% less flops. The DCFormer performs slightly worse on the instance segmentation tasks. This is probably due to the reduced feature map size and lack of high-frequency texture information. We finally conduct ablations on DCFormer with swing tiny backbone. We find that the DCFormer generalizes well to different backbones. The zigzag-based hard selection is the most effective and efficient way for frequency domain compression, comparing with the cross-attention and average pooling. The DCFormer is also more effective at the same flops comparing with RGB backbones with reduced input resolution. We notice the DCFormer and swing transformer with RGB input generates very similar activations in most cases. Again, demonstrates that the DCFormer is able to learn the semantics directly from the frequency domain representations. Thanks for your interest. Please read our paper for more details.